So it's really 7-3, not 8-3. 7-3. We're going to be solving trigonometric equations. Solving trig equations. Now, here are the steps to solving, and then really we just get to start practicing. So just like all other equations when we were isolating the radical, or isolating the logarithm, or isolating the base, we isolate the trig function. Trig part of the function should be isolated on one side of the equation. Unless it is quadratic in form. So if it's quadratic in form, we solve quadratics by getting them set equal to 0. So if that was the case, we do that. According to the unit circle. If you cannot solve it, if it's not a value on the unit circle, that's when we'll do inverses. And then it would be appropriate to not use your unit circle, but only if it's not on the unit circle of whatever it is. Now remember that this is important for today's answers. Remember that for sine and cosine, they have a period of 2 pi. What that means is after 2 pi, it starts repeating. So think about it. If I have some solutions on 0 to 2 pi and I go around again, it's going to be just a repeat of those same solutions, but now 2 pi more. Does that make sense, everyone? We repeat after 2 pi. So solutions will repeat after 2 pi for sine and cosine. Then for tangent, because tangent actually repeats halfway around the unit circle, tangent only has the period of pi. So our solutions will actually they'll repeat every pi amount of time, not 2 pi. All right, so once again, a period is the length of one cycle before it starts to repeat the same thing over and over again. Okay, here we go. So just a reminder of sine, cosine, and tangent of what they look like so you can keep in mind what their inverses look like. Here is sine. How do I know? 0 max, 0 min, 0. Isn't that the pattern for sine? So our domain is all real numbers for sine, and then our range is bouncing between -1 and 1. For cosine, how do I know it's cosine? Max 0, min 0, max. So that domain is all real numbers. We can go around the unit circle as many times as we want, correct? But it is bouncing between -1 and 1. And then tangent has asymptotes split evenly over the y-axis. So we would say for tangent, x cannot be this value or this value. That's where it's divided by 0. That's what creates an asymptote that's vertical. And then, but our range is -infinity to infinity. So with that in mind, it kind of helps you remember how the inverses look as well. Okay, here's our first example. Let's just go for it. So, isolate the trig function. That means get the trig function all by itself. So there's 2 trig functions. We want to put them on the same side. So we're going to add sine of x to both sides. So now we have this. 2 sine of x plus root 2 equals 0. Now your first step is to get the trig function all by itself. So I'm going to subtract root 2. 2 sine of x equals negative root 2. Then I'm going to divide by 2. So we're looking for when does sine of technically x in parentheses equal negative root 2 over 2. Yeah, so now we're solving. We're finding all of the values that will make this a true statement. So cosine is x, sine is y, tangent is y over x. This is a value on the unit circle, so locate it. Cosine is x, sine is y. So find a y value that is negative root 2 over 2. Doesn't it happen right there? And right there. True? And then as I go around the unit circle backwards, wouldn't I hit it right there? And right there. And if I went around once and I went around again, wouldn't I hit it there and there would be the same thing? True? So our answers are x is equal to 5 pi fourths and x is equal to 7 pi fourths, but it says find all the solutions. So plus or minus 2 pi, and we can add that 2 pi as many times as we want. That's a coterminal angle. Wouldn't that line in the same spot? So plus or minus 2 pi n number of times. Plus or minus 2 pi n number of times. So if we think about it, our first one would be when we plug in 0 for n, because that would be our first solution, since that would become 0. We plug in 1, that would be starting at the first solution, add 2 pi, and you get right back here, and you could do that as many times as you know what I mean? If I said find the solutions on an interval from 0 to 4 pi, you could do it this way, and then you would just add 2 pi once. Add 2 pi once. Does everybody get what I'm saying? Okay, cool. Easy stuff. Okay, isolate the trig function. So we would add 1, divide by 3. I'm going to do 2 steps in 1. Does everybody see why I'm adding 1, then dividing by 3? Yeah? So we would have tangent squared of x equals 1/3. Just like a quadratic, we would square root both sides. So we have tangent of x is equal to, if you have a fraction in radicals, you split it up, root 1, root 3. So that's when does tangent of x equal 1 over root 3, which rationalizes to be, when does tangent of x equal root 3 over 3. You'd have to say, and you should be at this point starting to get these kind of memorized, is tangent is y over x, first of all, y over x, and root 3 over 3 is a tangent value on the unit circle. So if you'll remember, look, that divided by that, y divided by x simplifies to be a root 3 over 3. Do the math if you need to. We've done this a million times this year, though. That divided by that simplifies to be root 3. So do you remember how we talked about this? You need to be having these memorized. Root 3 divided by 3 is smaller than root 3 because this one's not divided into 3 pieces. So that goes with the smaller angle. So wouldn't this be also root 3 over 3, just possibly negative? Okay, cool. So you guys get what I'm saying. The bigger one goes with the bigger answer. Okay, cool. So our answers are x is equal to, where did it happen in the first place around the unit circle? Pi 6. And then also, and 7 pi 6, technically, if we wanted to be technical on the first way around the unit circle. However, think about it. Couldn't we start here and just add pi in length and get halfway around? Isn't that when it starts repeating, everybody? After pi for tangent. So then you add pi and you'd be back to here. Isn't that good? Yes. So we only need to list out the first solution because it starts repeating after pi. So it'd be pi 6 plus or minus pi, the number, however many times we want to add pi. Does that make sense? For tangent, it's only pi. Okay, so with this one, we isolate the trig function. So we're going to bring 2 cotangent of x over by subtracting. So now we have cotangent x cosine squared x minus 2 cotangents of x equals 0. Now with this one, we can factor out a cotangent of x, true? If we factor this, we can set it equal to 0 and solve. So let's go ahead and factor out a cotangent of x. Look, here's our first term. Here's our second term. What's in common? Cotangent. Does everybody see why I'm choosing to factor out a cotangent? So I pull out cotangent of x. So then divide by cotangent x, cotangent of x. Let's see what's left in our parentheses. Cosine squared of x minus 2. Now, just like factoring a quadratic, the zero product property rule says if we have factors that equal 0, then we can set each of those equal to 0 and just solve them individually. So now we'll literally go, when does cotangent of x equal 0? When does cosine squared minus 2 equal 0? So let's solve for each of these. Remember, cotangent's the reciprocal of tangent. Tangent is y over x, so this is x over y. So when on our unit circle does our x value divided by our y value become 0? Right here, right here, right here, where? Which one? Oh, I just did y divided by x, didn't I? Didn't I just draw y divided by x? Shouldn't it be backwards? Fix that. So it should be this, and this. Which one equals 0? Pi halves, correct? 0 divided by 1 is 0. Isn't 1 divided by 0 undefined? So our solutions happen here and here. But once again, with cotangent, because it's the same as tangent, can't we just say this solution and then only add pi? Add pi, we're good. Okay, so our answers are x is equal to pi halves, and then plus pi as many times as we want, plus or minus pi as many times as we want, pi n. Now let's do this one. So we would add 2, so we have cosine squared of x equals 2, then we would square root both sides. So cosine of x is equal to plus or minus root 2. Is there a root 2 on our unit circle for x? No x value equals plus or minus root 2. So this is not on the unit circle. So this would be an appropriate time to solve for x by cosine inversing both sides. So we have x is equal to cosine inverse of plus or minus root 2. You would treat them separately. So we're really looking at this. X is equal to cosine inverse of positive root 2, and x is equal to cosine inverse of negative root 2. Now remember, because we're solving this way, inverses do have restrictions that we can plug in. We can only plug into cosine and sine inverse between numbers between negative 1 and 1. Is root 2 greater than 1? Root 2 is 1.4. So isn't that too big to even plug in? And if you tried in your calculator, it's going to say error. So it doesn't work. So we would throw that solution out. Well, negative 1.4 is smaller than negative 1. So it's too large on the negative end. Does that make sense? It's outside of our input. So we'd also cross out that solution. Therefore, this is our only solution. There's many solutions, but that's the only place that is true. Okay, next one. Make sure please ask questions if you have them, because I sometimes don't know if I've answered everything. So cosine inverse has an interval that you can only plug in things for cosine inverse between negative 1 and 1. So root 2 is 1.4, which is too big. But once again, even if you forgot that and tried to plug it into your calculator, it's going to say error. So then you would be like, what's going on? We must not be able to do that. Does that make sense? Great question. Okay, next one. 2 sine squared minus sine of x minus 1 equals 0. This one we would not isolate the trig function. Here is why. It is quadratic in form. So we solve quadratics by getting them set equal to 0 and solving by factoring. So this is why we learned how to factor these last time. All 4 today to be able to solve. So you're going to do a U-substitution. Let u equal sine of x. So then we have 2u squared minus u minus 1 equals 0. So now do you see the point of why we were doing that last time? What multiplies to be a times c, what multiplies to be negative 2 and adds up to be negative 1, 1 times 2, negative 2. We can't quick factor, so we would drop and break as quick as possible. So I'm going to put the negative 2u first, the plus 1u next, factor by grouping. So I'd pull out a 2u, so then divide by 2u, u minus 1, pull out a positive 1, u minus 1, my safe haven's the same, so I factor out u minus 1, left is 2u plus 1. Now we'd say, but that is really not what we're looking at. We're actually looking at sine of x minus 1 times 2 sine of x plus 1 equals 0. So now that we have it factored, we can set each of those equal to 0 and solve. So we would say, when does sine of x minus 1 equal 0? So when does sine of x equal 1? We would subtract, so we'd have 2 sine of x plus 1 equals 0. Subtract 1, divide by 2. So when does sine of x equal negative 1/2? Cosine x, sine is y. So let's look. Y, boom, right there. True? Anywhere else? That our y value is 1? Nope. So x is equal to pi halves. And then did it say on an interval? Oh, it says on an interval from 0 to 2 pi. So it only wants the first solution on that first unit circle. So we're good with that one. Now, sine equaling negative 1/2. Cosine x, sine is y. So right there and right there. No. So then we also get x is equal to 7 pi 6. And x is equal to 11 pi 6. And that's our interval from 0 to 2 pi. So we have 3 solutions on this one. Another one? Okay, so notice in this one we have secant squared x minus 3 secant x minus 2 equals 0. How do you think we should do it? A U-substitution. Something interesting happens here, though. Let's go for it. So you're right. U is equal to secant of x, so that we have u squared minus 3u minus 2 equals 0. We go to factor it. What multiplies to be -2 and adds up to be -3? 1 times 2. Uh-oh. These would both need to be negative, making that positive. This is a non-factorable quadratic. We have to use the quadratic formula, so make sure you use U. U equals -b, +3, plus or minus the square root of b squared minus 4ac all over 2a. So 2a is 1. I'm just going to write that. So u is equal to 3 plus or minus the square root of 17 all over 2. But we're not solving for u, are we? We're not solving for u. We got to put that bad boy back in. So we're looking at this. When does secant of x equal 3 plus or minus root 17 over 2? Now my question for you is that even on the unit circle? No. So we're going to be able to inverse both sides, true? Okay, so we would say, okay. So we could our secant inverse. Secant inverse. So we have x is equal to secant inverse of all that stuff. We cannot do secant inverse in our calculator. What does secant inverse really mean? 1 over cosine. So we're really looking at this. X is equal to 1 over cosine inverse of all that stuff. Is everybody with me? Now here is the question. We have to split these up because this is really this. X is equal to 1 over cosine inverse of 3 plus root 17 over 2. And it's also x is equal to 1 over cosine inverse of 3 minus root 17 over 2. So can we even plug it in? Let's see. Can you plug in both, not both? Well, which one? You said no too? So when you plug this in, you've got error, because that is larger than 1, everybody. We can't do it. Cross it out. What about this one? Okay, awesome. Now here's the next thing that we have not been saying first or second hour. We're answering in radians, so your calculator needs to be in radian mode. Thank you, that's right. 0.46. So that would be our answer. This would be the exact answer. So you could circle both, because one's an exact answer, one's a decimal answer. I think it just depends. In your book, sometimes they leave it and sometimes they do the decimal. Yeah. Yeah, so you would calculate cosine inverse of all that stuff, and then you could do 1 divided by second answer. As long as you can put parentheses in the right spots, you're good. You want a second to see if you can type it in right? Yeah. Okay. Something new, once again, that's happening new to us. So 2 sine squared x plus 3 cosine of x minus 3 equals 0. This one we can't do a U-substitution because there's sines and cosines. So just like last time we talked about, we would either want all sines or all cosines so that we can do a U-substitution to factor this. You can't change cosine to be sine because it's not squared. So do you see how we have a sine squared? Can we rewrite that in its equivalent form but as a cosine? Trig identities, yes. So what is this? Literally the exact equivalent thing. What is that? Can I replace that with its equivalent statement? You're saying that's 1 minus cosine squared of x. Yes, that is true. We have not changed the problem because they are equal, equal, equal. Does everybody see? So I'm just rewriting it as its equal form. So we have 2 times 1 minus cosine squared of x plus 3 cosines of x minus 3 equals 0. I'm going to take 2, distribute it in. 2 minus 2 cosine squareds of x plus 3 cosine of x minus 3 equals 0. When solving a quadratic, we would want to put it in standard form and combine all like terms. So we would have -2 cosine squared of x plus 3 cosines of x. Can't combine those. Squared with a 1. But then isn't this +2 minus 3? Which is? -1 equals 0. Now, I personally don't like the negative in front, so I'm going to factor out a -1. So I would divide each of these by -1. So then we would have 2 cosine squared of x minus 3 cosine of x. And then plus 1 equals 0. And then because this is just -1 with no variable, it won't affect your solutions, correct? We know that. So let's just forget about that for we're solving. We don't need it. It is there if we're factoring it, but you get what I'm saying. No variable. Okay, so let's factor this. So this would be 2u squared minus 3u plus 1. Ready, go. You factor it. You can go quicker than we can do it together. I'm just going to ask for the factors. What is the factor to be? Okay, so then we have 2 cosine of x minus 1 times by cosine of x minus 1 equals 0. Set each of those equal to 0 and solve. My unit circle is going to have to go away. So we'd say 2 cosine of x minus 1 equals 0. So when does cosine of x equal add 1 divided by 2? Does everybody see why I'm jumping there? Because I don't want to keep you too long if possible. So when does cosine of x equal 1/2? Then we'd say add 1. So when does cosine of x equal 1? Did it say anything on an interval? No, so we got to find all the solutions. Okay. So you guys told me based on your unit circles, x is equal to cosine x. So pi thirds plus or minus 2 pi n. What else? Do you guys know what you're doing? You're looking at your unit circle. You're finding the x values that are 1/2. Okay, cool. 5 pi thirds plus or minus 2 pi n, right? Okay, awesome. And then right here, when does cosine equal 1? I think there's only one spot. 0? 0 plus or minus 2 pi n. Now think about it. 0 plus or minus anything is just itself, correct? So they're not going to write the 0 there. So x is equal to plus or minus 2 pi n. Because we can plug in 0 for n. That would be our first one. Does that make sense? So they wouldn't write the 0. So there's your box of solutions. If they ever have a double dipping answer, they're not going to list them both, so you can always check that. Because I remember last year we ran into something weird, but it's because people were realizing, oh, well, this answer and this answer are overlapping. If we just did this one, it would take care of it all. So just watch out for things like that. But none of these overlap. You get what I'm saying? So we're good. Okay, cool. Let's do another one. Well, the bell's going to ring in 2 minutes. So maybe we should just wait. You could see if you could get started on some, but we'll come back. Okay, so with this one, we would square both sides. Now, guys, we've just changed the equation. That's okay, because if we had, for example, the square root of x plus 1 is equal to x minus 3, we could square both sides, right? But the more we start manipulating this equation, like changing it, you have to check for solutions. In all of our examples before, we just factored it, or we just, you know what I mean, we didn't change anything. Or we did change some things to be equivalent, but that's still not changing it. This is actually physically changing it, which is okay, but we got to check our solutions. So we know we can't break the forbidden rule here. So we have cosine of x plus 1 times cosine of x plus 1 on this side is equal to sine squared x. So then when we multiply this out, we'll get cosine squared plus cosine plus 2 cosines of x plus 1 equals sine squared. Now we want them to be all cosines or all sines. We can't change this cosine to be a sine, so let's change all the sines to be cosines. So what is this? 1, I don't even need parentheses, 1 minus cosine squared. So now you'd say this is a quadratic in form, so we're going to get it set equal to 0 and solve by factoring. So I'm going to subtract 1, add cosine squared. Subtract 1, add cosine squared. So now I have 2 cosines squared of x plus 2 cosines of x equals 0. Now we can solve by factoring, right? Pull out a 2 cosine of x, then divide by each by 2 cosine of x. So then left in our parentheses would be cosine of x plus 1. Then we can set each of those equal to 0. So set 2 cosine of x equal to 0. Set cosine of x plus 1 equal to 0. So aren't we looking for when does cosine of x equal 0? When does cosine of x equal -1? So that's pretty easy. Cosine x, doesn't that happen here? And here. But this is where I'm thinking, okay, we could put both of those, or couldn't we just put the 1 and add pi? Now that I think about it, that's what they're going to do. They're not going to, even though cosine has a period of 2 pi on that part, do you see what I'm saying? I would take care of it all. So you'd say plus pi halves, or x is equal to pi halves, and then, oh, it does say on an interval from 0 to 2 pi. So we will list them out separately. So then just 3 pi halves. And 3, that's a comma. That's a comma. And then when does cosine equal -1 at x equals pi? We have to check our solutions. There are going to be some extraneous. So we would take those 3 solutions since we manipulated it and check to see if they're extraneous by plugging it back into the very original. Okay, checking. X is equal to pi halves by plugging it in to the original function wherever there's an x. So you'd say, does cosine of pi halves plus 1 equal sine of pi halves? Let's see if it's a true statement. Cosine at pi halves is 0 plus 1. Sine at pi halves is 0 plus 1, 1. So we got to keep that one. It's not extraneous. Let's check 3 pi halves. So cosine at 3 pi halves plus 1, does that equal sine of 3 pi halves? Cosine of 3 pi halves is 0 plus 1 is equal to sine at 3 pi halves. -1. True statement? No. Not a true statement. So it's extraneous. Then we'll check pi. The cosine at pi plus 1, does that equal the sine of pi? Pi is cosine of pi is -1 plus 1 is equal to sine of pi is 0. 0 equals 0 is true. Check your solutions if you manipulate both sides of the equation. All good? Next one. Okay, so notice this one's different because this is the first time we're seeing a 3 in front of t, right in front of the variable. So you cannot do this one. You can't just get rid of that 3 and then solve it. It's stuck inside. So what we're going to do is we're going to solve it like normal, and then we'll worry about the 3. So just solve it as if it's this. 2 cosine of t minus 1 equals 0. So we're looking for when does cosine of t equal 1/2. Right there. Cosine x, where else? Right there. True? So we'd say, okay, so we have t is equal to pi thirds, and it didn't say on a certain interval, so plus or minus 2 pi n, and t is equal to 5 pi thirds plus or minus 2 pi n. But we were not dealing with t, we were dealing with 3t. Do you see what I'm saying? So it's really 3t. So now to get t along, we would get rid of the 3. So yes, you could say divide by 3, but let's think more advancedly about this. Just times it by a third. You gotta do both sides. Times by a third, times by a third, and then doesn't that take care of the 3? So we would have t is equal to, you gotta multiply a third in there and there, so that would be pi ninths plus or minus 2 pi thirds n. You get why I'm getting 2 pi thirds? And then t is also equal to 5 pi ninths plus or minus 2 pi thirds n. Because you would distribute a third in there and there. Okay, we're doing good. You guys try this one by yourself. Make sure you're good to go. Do it by yourself quickly. We only have like 2 more examples and we're going to go through them quick. We're able to get up to here at least. But it's not really, it was really x over 2 is equal to 3 pi fourths plus or minus pi n. So then we would times both sides by 2. So then x is equal to, if you distribute 2 in there and there, you're going to get 3 pi halves plus or minus, now it's 2 pi n. Okay. Do we have questions on that one? Yes. So you have to take 2 and multiply it into both terms. Yeah, good question. Is there another solution that we're not missing? So why did I not list that one out to begin with? It's a good question. Why did I not list that one out to begin with? Because it's tangent. Because so if we just add pi, won't that land there and take care of it? That was a great question. Yeah. Okay, cool. So we're almost there. So secant squared minus 2 tangent of x equals 4. Tell me how you would tackle this one. Yeah, you're awesome. So she's saying we need all tangents or all secants. She said this is 1 plus tangent squared. 1 plus tangent squared. That's equivalent. We did not change the problem. This one we won't have to check. Because that was the equal. We didn't change it. Minus 2 tangents of x equals 4. It's a quadratic in form, so we're going to want to get it in standard form and equal to 0. So I would have tangent squared x minus 2 tangents of x, and then I'm going to subtract 4 over. Negative 4 plus 1. Negative 3. It multiplies to be negative 3, adds up to be negative 2. 1 times, I'm doing a U-substitution. So negative, right? U plus 1, U minus 3. So we would say so then we could set each of those equal to 0. So when does tangent of x equal negative 1? And then we'll do when does tangent of x equal 3? I added 3 over. So this one is on the unit circle. Tangent equals negative 1 at here again, right? And at 7 pi fourths, but once again, if we add pi, it's going to take care of it. So x is equal to 3 pi fourths plus or minus pi n. Then when does tangent equal 3? 3 is not on the unit circle. Root 3 is, but this isn't. So this would be appropriate to take the tangent inverse. So x is equal to tangent inverse of 3, which you can plug anything into tangent inverse if you remember. And that's how they might leave the answer, but they also might type it into their calculator in radian mode. So x would be the decimal of whatever that is, tangent inverse of 3. Thank you. Okay, cool. Pretty easy. Okay, that's the last example. So I need you to work the rest of the time. Here's what I'm worried about.